Okay, so ladies and gentlemen, chapter 21 is all about nuclear chemistry, and we are not going to cover the whole chapter. We're basically just going to cover, honestly, the parts that I want to cover. So, you know, everything we have done in chemistry so far has fallen into two categories. Every process that we've done has either been a physical change or a chemical change. There is a third category, nuclear reactions, which, as the word sounds, nuclear, it has something to do with the nucleus. It's making changes in the nucleus. Okay, and no chemical reaction that we have looked at has had that occurring, changing the nucleus. Okay, so when you go through a nuclear reaction, we call it radioactive decay. Okay, we're making changes to the nucleus. The nucleus undergoes some kind of decomposition of some sort. It loses something, or something changes about it. But the point is, you get a different nucleus, which means your product is a different element. And that's something that is very different from a physical change or a chemical change. We have never had reactions where an element changes into a different element. Okay. Now, are all elements radioactive? No, they're not. Okay. First of all, guys, you may or may not have seen this word before, nuclide. A nuclide, that word just means some sort of radioactive particle, okay, or a radioactive element. Elements that have an atomic number of 84 or more are automatically considered radioactive elements. So on your periodic table, any element above 84 is naturally radioactive. If you were to dig around in the dirt and find the element uranium, for example, that's one we'll see a lot, it would automatically be naturally radioactive, very unsafe to be around. Okay? But it's not actually the protons that make something radioactive and very unstable. It's actually the neutrons that are responsible, or to be more specific, the neutron to proton ratio is what makes an element radioactive, very unstable. And if you think about it, you know, elements towards the top of the periodic table, like boron, carbon, nitrogen, oxygen, elements at the top of the table, their number of protons is very often the same as the number of neutrons. But as you start moving down the table, or, you know, getting more elements with more and more protons, the number of neutrons of those elements starts to outweigh the number of protons. Okay? It stops being a one-to-one. Okay? And so what you end up getting is elements at the bottom of the periodic table have many more neutrons than protons. So that ratio starts climbing above 1. And when it hits a certain number, you don't need to write this down or anything, but I think when the ratio hits like 1.51, then that's considered unstable radioactive. Okay? We are going to look at 5 types of radioactive decay, most of which you've probably seen before. Here's our first one. You can call it alpha production. You can also call it alpha decay. All right, so what we would have, a radioactive nuclide. This is an atom of uranium. It undergoes a nuclear reaction, and we get a new element. This underwent alpha decay. So here is an alpha particle. Ladies and gentlemen, it's not a helium atom. It's just a helium nucleus. So what doesn't it have? Electrons, yeah. An alpha particle is 2 protons and 2 neutrons in a little bundle. That's all it is. Okay? And sometimes, guys, these questions will be as simple as fill in the blank. Like, maybe you're given an equation, but what's in the blank here, there's nothing there. And you're supposed to fill in what's there. Treat the arrow like an equal sign. And then the numbers will match up. 92 equals 2 plus what? 90. 238 equals 4 plus what? 234? How do you know what element symbol to fill in there? Yeah, the atomic number. Element number 90 is thorium. And that's all you have to do. Is just fill in the blank. Okay. So alpha decay is one type of radioactive decay. Here's another that you're probably familiar with. Beta decay or beta production. Do you all know what a beta particle is? What is that? It's an electron. Yeah, a beta particle is just an electron. But again, just like any other nuclear reaction, you have one element changing into a different element. That's very characteristic. That's unique to nuclear changes. Now, guys, full disclosure here. Nuclear chemistry is not my area of expertise. And something that goes on in beta production, I know what's happening, but please don't ask me why it's happening, because the answer will be, I don't know. So here's what's happening with beta production. It says, a neutron changes into a proton. Please don't ask me how that happens or why that happens. I don't know. But the math supports that. Okay, remember, or you guys tell me, what is this top number called? Like if this is the atomic number, what's this? Mass number. Do you remember what that is? The number of protons plus neutrons. Okay, well, now look at the numbers on the other side. We have gained a proton, but one of this proton came from a neutron, so the total neutron and proton count doesn't change. So the math supports this, but again, I have no idea how or why that happens. Okay, but that's beta decay. So there's alpha, beta. Do you guys remember what's the third one you always hear about? Gamma. Okay? And I want you to notice it doesn't say like a gamma particle. Okay? Gamma decay, and this font is not great. That's kind of how I draw it. That's the symbol for gamma. Notice that it has the numbers 0 and 0. Okay. If you want to ignore this coefficient here, you can. But the point is, it's not a particle. It's a ray of energy. Okay. The only reason that 2 is there is just to say that every time this reaction happens once, you get 2 releases of gamma radiation. Do you see anything else in that equation that looks familiar? Yeah, there's an alpha particle. Okay. Well, I want you to keep in mind something, okay, that gamma ray production always accompanies another type of decay. You don't ever have gamma decay just by itself. You know, gamma radiation happens along with alpha decay or along with beta decay. All right, but it's just a release of excess energy to return your element, your atom, back to ground state, the lowest energy form. Okay? So those 3 types of radiation, all of you should have learned in Chem 1. You may have learned these other 2. I don't know. Here's another one. Positron emission. Now, what the heck is a positron? Well, a positron is a positively charged electron. Please don't ask me how that exists. I don't know, is the answer. Okay. But just like all the others, we have an element changing into another element. Okay, and guys, if you think about it, if a positron is just a positively charged electron, this process is kind of like the opposite of beta decay. This time, don't ask me why, we have the opposite process happening. A proton morphs into a neutron. Okay, but it's just another form of radiation. There is a 5th and final type called electron capture. Okay. This one is different than the other 4. In case you hadn't noticed, the other 4 always have the radioactive particle or energy, whatever it is, on the product side. This is the only one that has something special on the reactant side. But it's easy to remember, guys. Think about what the word capture means. If a person is captured, they're taken and kept by somebody else. They're not released. Okay? Electron is not released or produced. It's taken in. It's on the reactant side. Do you see something else up there that looks familiar? Yeah, there's a gamma ray. Okay? Electron capture always will release gamma radiation. Always. Okay? Alpha decay sometimes releases gamma radiation, sometimes it doesn't. Beta decay sometimes releases gamma radiation. Electron capture always does. Mm-hmm.
How do we know how much gamma radiation is produced?
You don't. No. Are you thinking like that coefficient?
Yeah.
I have no idea. No. To be honest. Okay. So let me tell you what your job is. This is so simple. You are going to write some equations or fill in the blank. Okay. Let's do number 1 together just to make sure that you are comfortable with this. Okay. First of all, guys, I know you've seen this notation before. I just want to make sure you understand it. When you see notation like this with an element name, a dash, and a number, what is that number? It's the mass number, protons plus neutrons. And when you're writing like the element symbol, number, which one is it, bottom or top? Top, okay. So it says chromium-51 decays by electron capture. So chromium-51, and what is chromium's atomic number? Someone tell me.
4.
What is it? 24, okay. And it's electron capture. Remember, that means it's on the reactant side. Treat the arrow like an equal sign. Everybody, what's 24 plus -1? Very good. What's 51 plus 0? Okay, so what element is that? It's V, vanadium, or vanadium, whatever. Okay. Anything else that needs to go in there? A gamma ray. 0, 0, and there you go. That's it. Okay? You guys do the rest. Okay, check your answers. I'm sure they're all right, because this is very, very simple. Okay? Let's talk about some real-world situations where these reactions actually do occur. And first and foremost, it's not the most pleasant topic to discuss, but radioactive, nuclear weapons is probably the most common place that we hear about radioactive decay. And something that you all need to know is most of these reactions do not occur just one time, okay? Most radioactive decay situations are a series of reactions, like a chain reaction of reactions. And this is exactly how, like, a nuclear bomb works. Okay, like a uranium bomb, this is how it would work. You start with this radioactive element, and it undergoes a series of alpha decays, beta decays, until it reaches something like lead, for example, that is what they call stable. It is not a radioactive substance. Okay? And so this particular, what they call decay series, every time you see a blue arrow, that represents an alpha decay, and anytime you see a red arrow is a beta decay event. Some of you that took honors, I'm not sure if the honors teachers do this anymore, but we used to give you the starting nuclide and ask you to predict, does it go through alpha, does it go through beta, and we made you write out these sometimes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 step reactions. Okay, I'm not going to make you do that. Okay, but guys, this is exactly how a nuclear weapon works. Okay, now here's the thing. These radioactive particles, like an alpha particle, a beta particle, some are more dangerous than others. The smaller the mass, the more dangerous they are to humans, okay? The smaller the mass, the term they use is the greater the penetrating power. What radioactive particle of the 5 types of radioactive decay that we saw, which one has the greatest mass? An alpha particle, because it's 2 protons, 2 neutrons. Guys, you could block an alpha particle with a piece of paper. So it's not very dangerous. What would be next in size? A beta particle. And what is a beta particle? It's an electron, okay? An electron could go through a piece of paper, but you could block it with, like, a lead vest. You know, when you go and you get an x-ray and whatever part of you is not being x-rayed, they make you wear those lead aprons or something like that. That's to block that radiation from anywhere in your body that's not being x-rayed. Okay, a positron is the same thing as an electron, just with a different charge. What's even smaller than that? A gamma ray. It's not a particle at all. It's a ray of energy, and that is the most dangerous, and that is the real killer of nuclear weapons. Every time these alpha and beta decays are occurring, gamma radiation is being released right along with it. And guys, gamma radiation can penetrate pretty much anything. And when it passes through the human body, it tends to target your DNA, which is not a good thing because it causes deletions, mutations, all kinds of things like that. So if we want to think about an event in history, like one of the bombs that the United States dropped on Japan at the end of World War II, one of them was a uranium bomb, the other was a hydrogen bomb. think. Okay? And, you know, first and foremost, it's a bomb. It's something that explodes. So it releases a big shock wave. So anytime you have a bomb, there's a shock wave, people die from the blast, a building falls on top of them. But the thing that makes nuclear weapons so dangerous is that you don't have to be that close to the detonation site to be affected by it, okay? Because you get this blast of gamma radiation, which you can't see, okay? People that were relatively close to the detonation site, they might have gotten such a big blast. I mean, this is really graphic, but maybe a building didn't fall on top of them, but they were hit with such a huge blast of this gamma energy that they were vaporized. Like the entire human body in a second, vaporized. People that were a little further back, you know, had actual burns on their skin. People that were further back from that may not have immediately seen any physical effects, but again, it tends to target your DNA. And this is just something that a medical doctor told me one time. Anytime you start messing with a person's DNA, it pretty much always will lead to some form of cancer. So a lot of these people that maybe at first felt like they were saved and they were not affected by these nuclear weapons, they really were, they just didn't know it yet. And in fact, a lot of the scientists that worked on the Manhattan Project, my great uncle was one of them. It was actually really cool to hear his stories, but he worked out in the deserts of Los Alamos, New Mexico, where they tested these bombs before they dropped them. He died of cancer. All of his colleagues died of cancer. They just didn't know. They didn't know about how devastating this radiation would be. They thought that if they were 2 miles away from the drop site, that would be a safe enough distance. It wasn't. They thought that if they were inside a building, they were safe. It wasn't. There are, I mean, material can block gamma radiation, and I actually Googled it, but it's pretty substantial. Like, I want to say, you know, in order to block gamma radiation, you have to be behind like 5 feet of concrete or something like that. So how many buildings are made with 5-foot thick concrete walls? Not too many. Okay. So it's the gamma radiation that's really damaging. Okay. But this is how nuclear weapons work, and that's why they are so devastating. Okay. So there is some math with this, although we've actually already done the math, you just didn't know that you were doing it. We have an equation here, which might look unfamiliar to you. Let me write it a different way that will look familiar to you. Or I hope will look familiar. Does that look familiar at all? On your equation sheet, you have something that looks very much like that. That is the integrated rate law for first order reactions. The only difference is on your equation sheet, it doesn't say N and N naught. It has brackets with molarities in this place. But here's the thing, guys. All nuclear or radioactive decay, nuclear reactions, obey first order kinetics. All of them. Which means we can use this rate law. This does not have to be a molarity. It could be an amount in grams. It could be a number of atoms. If I have 50 grams of uranium and 10 minutes goes by, remember T is time, and it decays, how much uranium is left? You can use this equation just like that. Okay, so there's nothing to memorize here. You already have this equation. And when we did kinetics, guys, we also looked at half-life, which you can look at as well. Don't memorize it. This equation is on your equation sheet. Do you remember what this lowercase k is called? Yeah, it's just the rate constant. Okay? So we can do math with this. And in fact, let's do number 2 together. All right? It says, how long does it take? Stop there. How long does it take? What is our unknown? Time. Okay? So T is my unknown. For a sample of cobalt-60 to decay down to 16.5% of its original mass, the half-life is 5.26 years. Okay? Well, let's use that integrated rate law equation. Okay? If we're looking at a percentage, ladies and gentlemen, what do you think is a really easy number to work with as my original? 100. And we're supposed to figure out how much time has gone by when it gets down to 16.5%. Okay? T is my unknown. How am I going to get K? I need that. Use the half-life equation. Can you tell me what the units would be for that rate constant? What's that? Yep. An inverse year. Okay. So now let's plug it all in. So that was number 2. I'm going to have you guys do numbers 1 and 3 on your own. Go to it. So that's it. Okay. That is all of nuclear.